Hi, my name is Alex Pinto, and this is Defending Networks with Incomplete Information, a machine learning approach. This is the launch presentation of the MLSec project, and it took place at the DEF CON and Black Hat conferences on 2013. So, before we start, I just wanted to talk a little bit about myself. I've been in the information security industry for 12 years, and as a principal consultant in a large consulting firm, I got a chance to do pretty much everything. But most of my time there was leading and actually consulting technically in information security monitoring teams. So any projects that would range from setting up SIMs and SOCs and putting together the teams that would manage them, either on an internal SOC in the company or in an on-premises SOC. I'll be involved in pretty much of them. And that got me exposed to a lot of technologies in the SIM space and also made me and allowed me to try out all different techniques, all different configurations in order to set up those teams and try to generate some value from the log files that the organizations are hoarding today. So after doing that for a while, I recently took some time off and I decided that I should do something different. And after studying for a while to machine learning, data science, it quickly became obvious to me that there could be a good way where these two different knowledge areas could interact and potentially bring some good to what we're doing here in information security and try to help with a few of these challenges that we see every single day. I mean, anyone who has been doing security monitoring for a while understands that it is a very hard problem in all sorts of different dimensions, not only for the amount of the kind of tools that we have to do the job, but also around appropriate staffing and making sure that we have the right people and we have the people that are properly, not only the people who are properly trained to do that, but also the right amount of people to actually handle the amount of information we have to work with. So we pretty much start out this journey by talking a little bit about the state of security monitoring, and in a way why we believe that there is a gap there from the tools that we have and for the amount of trained professionals we have in relation to the challenge that we're facing. Then we give a brief introduction on machine learning, just to make sure that we are not just hand waving and telling you that machine learning is something magical that will solve all your problems, but to really try to bring down to earth what are the capabilities of machine learning and how it could potentially help. We touch on a very important point about data gathering and specifically adversarial environments in InfoSec, which is currently one of the biggest challenges in making machine learning work for information security. And then we delve into a case study, which is pretty much the discussion and the description of one of the algorithms that we put together on MLSec project, so that you can see a real life example of using those techniques to help us better manage and monitor our security infrastructure. So, well, let's get started. So, we'd like to start out by talking a little bit about the current state of information security monitoring. So, anyone who has been doing this for some time will tell you that one of the biggest challenges we have now is the sheer amount of information and logs and security events that we have. And a fundamental change that happened on this field for the last 5 years is that now pretty much everyone, doesn't really matter what size of a company you are, will have some sort of log management solution or a SIM solution where they will be gathering logs from servers, from applications, from their information security tools. And this has changed primarily because of PCI, HIPAA, and some other regulations that are really pushing the need of having this data stored for forensic purposes. So if there's a breach, at least we could potentially look at these events and try to figure out what really happened. So, I mean, you get all sorts of certifications, you get all sorts of manuals on how to do this logging. And like I said before, people would be primarily using information security tools like log managers, and SIM solutions. And a point that we see time and time again, and this is based on a little bit of research that I did on analyst documents. I mean, if you look at Gartner, the recent one, which was released in 2013, there will be a lot of text around how people are generally unhappy with their SIM infrastructures and how they're looking for a different solution, or they're going to change the solution. They're going to completely overhaul the solution because they're not getting the value they want at. And also, many companies complaining that about 93% of breaches they couldn't just detect soon enough, although that would be the reason why they would get a SIM solution there. But the one that really got to me, the one that really surprised me, was this graph here that you see. It's from a SANS document, which came across last year, which pretty much says what are the hugest pain points and what are the challenges that companies are seeing when they're integrating the log infrastructure. And the first one right there is just incredible. They're pretty much saying that their biggest challenge is to be able to use a SIM solution to identify key events from normal background activity, which is pretty much the point. It's pretty much the reason why you would have a SIM solution that is using their correlation rules, their prioritization techniques in order to get you in the front of what you would need to do and analyze. I mean, a valid comparison here would be something like, I bought a car, and my biggest problem with the car is that it can't get me from point A to point B. It really seems that something is missing. It really seems that whatever tools and techniques we put together around the specific technology, it's not really hitting the spot and making sure that we can use them effectively. And one of the reasons why that is although a great advance was made when people started using correlation rules for prioritization and for using this alert-based monitoring infrastructure, they're still very prescriptive. They're still very, I'd say, simple against the challenges that we have to face day by day. So if you look at a SIM solution, you invariably have two kinds of rules that you can use in order to express the complexity of the things you're trying to detect. So you'll either have a rule where you can pretty much fire an alert if something happens X times, and X is this magical number that will come from the factory settings, and you'll spend, I don't know, 3 months trying to figure out what this X should be in order for you to have an effective monitoring platform. Or you're creating rules where something happened and then a different something happened, where these two events, they have some sort of relationship, be either this event happened right after this one, or they come from the same IP address, or they're directed to the same IP address. So anyway, you can use any sort of field that those tools are mining, and they're normalizing in order to guess that to put together these rules. And of course, you could create arbitrarily complex rules by nesting those kinds of constructs, and to create whatever you want. The point is, you're pretty much iterating on those two until you can get something that makes a little bit of sense for you and for your customer. And that is usually very, very difficult to do, because although these rules are very prescriptive, they're very fixed in their capability, you will be running them against an enterprise or even a smallish company where all the business needs are fluid and things are changing all the time. And especially if you have an environment which is taking care of is doing development the way development is done now with agile techniques, they will do commits and they'll be changing their application 2 or 3 times each day. So it really doesn't scale properly. Some advance was done with behavioral rules, where you can try to figure out what normal is, so you can better define what those axes should be. but there are some limitations on these techniques. For anyone who has used them will know that very well. But it still makes the process very, very time consuming. And but I guess the point here is that even with all those challenges, there are some professionals who will do a very, very good job with those tools. And I've seen a few implementations, especially in large customers, that they will be not shy. They will understand those challenges. They will want a quality product out of this. They will want a quality deliverable, and they won't be shy to spending the money that would be necessary. I mean, I've met people who, in teams of two or three, in I don't know, 6 months to a year, they can really, really create a very, very good infrastructure that will really help the customer in their current state in order to make this happen. But although there's all these people with this amazing log management capabilities, as you can see by the picture there are not too many of them, and it makes it really hard for this concept of using those tools this way to actually scale and really help companies in the long run. It creates this schism where very, very, I mean, companies who have the money to spend, they will do well and they will pay for that. But the other ones, they will be spending money on the tool, but they will not be able to extract the full capability of what it can offer. And I guess one of the challenges that we're facing now, and bear in mind, I do not think this is a bad move at all, because of the amount of log data that we're starting to gather. We could be, especially in the largest environments, we could be seeing a necessity for using big data technologies to support this log management and even the rule creation. It will make it increasingly hard for us to find professionals that will be able to actually use these tools properly. So, and I'm not just talking about the infrastructure. So the same way in a traditional SIM tool, you might have a very big relational database, or even a columnar database in some of the recent offers that we've had. The large enterprises, they will have DBAs, they will have support IT people that would potentially help the analysts and the people who are configuring it. So actually running a Hadoop cluster or some equivalent for big data technologies is not really the problem, but the actual way you interact with the database and the knowledge structure is a little bit different, and there's a whole new area of knowledge that's being structured around that, which is heavily dependent on statistics, which is pretty much being called data science as of now. That is better equipped to deal with the massive amount of data and to be able to extract meaningful relationships from what's there. So on one hand, we have this very, very specialist information security analysts, which are currently doing a good job. And now you're pretty much requiring them to be able to learn statistics and also be able to perform in a data analysis and data science environment uh, with um, with some sort of fluency. And I mean, if we had a problem before, this problem is going to get much, much harder. There will be less and less people who will be able to make sense of this uh, deluge, right? This huge amount of logs that we're seeing, and this is one of the points here that we're trying to make. So maybe the solution is not so much to rely on human analysts, but to be able to rely on agents and analysts that are actually programs, and that will be they will help you prioritize what's going on in your log data. They will be constantly reading your logs. They're constantly making decisions based on the logs, and they will interact with the human analysts in order to make sense of all this data that we have available. Well, that all sounds great, but how do we accomplish this? And that's when we start talking about a little thing called machine learning. And you might have heard of this before. This is actually a concept that's been around for I mean, at least 40 years if you look at the most recent techniques that were invented. And there was really, in the 80s and early 90s, there was really a hope that people would hit this off and we would have like robots in the world with us now and thinking autonomously and making decisions autonomously. But one of the things that happened, and this is really interesting, is that people realized that they only really had the computing power and the amount of data that would be necessary for these algorithms that they created to perform is happening right now. So we're really having a renaissance of machine learning. And as I'll speak a little bit later, there's all sorts of applications and all sorts of ways that machine learning is now involved in our day-to-day lives. And the important thing about machine learning, why it's different, is that instead of instructing the computer on how to do something, instead of programming the computer to do a specific task, you're actually programming a way for the computer to understand different pieces of data, so you're providing it with information that you have categorized and you have separated to it in a specific way, and you're asking the computer to make some sort of decision based on the data that it gets. So based on this learning phase that it had before, based on the data that you use it to train it, once it sees new data, it will make a decision based on the data that it received, whether it should go this way or that way, or either what kind of intensity it should do something. So there's all sorts of different techniques, and I'll talk a little bit about that as well. So how are we seeing this? What's happening in our world today that is supported by machine learning? And I guess the most present example on everyday's lives comes from sales. So when you go to any e-commerce site right now, at least the biggest ones, you'll have a section there which is giving you some recommendations on what to buy. So based on what you have bought before, we have these items for you. And this is using a machine learning technique called collaborative filtering, which is pretty much inferring what you might like by comparing what you have bought on previous iterations on this website with a whole bunch of different other people that has bought there, which seems that you guys are similar. It's similar in the way the things you buy are pretty much the same. So if you bought a lot of books about machine learning, which is my case, you'll see introductory statistics there being recommended to me. It will look for other people who did similar things and see things and look for specific items that they bought, which I didn't. So, I mean, if we got so many things in common at first glance, so something that they bought would potentially be interesting to me as well. And it's very interesting mathematically. It calculates all sorts of distances based on who bought what, and it has this billion row matrix by billion column matrix that are multiplied all the time to try to figure out what are these proximity costs there, so that they can get to me which are the 5 items I would be most likely to buy if I was on a shopping spree or something like that. And ad networks that you see around there, they have a similar principle based on what you've clicked and based on the information that you have provided them. They try to guess and they offer the people who are buying the ads, okay, this guy has a high likelihood of buying from you. You should totally show this ad to them. Anyway, another big application is trading, and as of now, I mean, if you're trying to do trading as a sole investor, you'll always be outperformed by the higher players. And one of the reasons for that is because they have all of these trained algorithms, which are pretty much very in tune with all the time series data, all the historical data of what has happened from the beginning of time in the stock market. And they're making decisions in milliseconds whether to buy or to sell stocks. And also they're very, very close to the wire there. They pretty much sit beside on the same data center as the machines that actually runs the bidding mechanism, just to make sure they don't get offset by the speed of light. It's quite fascinating the way they do it. But the point is, right now you have algorithms fighting with algorithms, and there's a very big cautionary tale, and this is what this image illustrates, was when we had the flash crash. and NASDAQ and Standard & Poor's and pretty much Dow Jones and everything, right? Where one of these algorithms just lost control. It saw something in the noise. It thought like the market was crashing or something like that, and started very, very aggressively selling everything it had. And the other algorithms that were around, they saw this happening, and they felt like, okay, there's definitely something going on. So they started selling as well, and we lost like 5% in a few milliseconds. And hopefully there was some fail safes, and they backed out. But for a moment there, they just lost control. That's the closest thing we had to a robot uprising so far. They could potentially have crashed our whole economy just by making a poor decision. But anyway, not to worry. I'm pretty sure the guys are looking at it, right, guys? Right? This never happen again. Anyway, on a lighter note, there's been a lot of advancements in image and voice recognition, which are pretty fascinating. And the guys in Silicon Valley are really spearheading this. And this specific example is a very interesting example from Google from this year, where they started working with a new sort of knowledge-based algorithm, which is called deep learning, which uses a technique called deep neural networks, which is it's pretty much magical as far as us humans are concerned, but it uses the same old neural network concept from machine learning, which we have been learning for ages now. But the neural network creates itself, which is kind of a parallel to the way our brain, or at least the way we think our brain works. So it's very promising. And what they show here is that they used a cluster of 16,000 machines or something like that to teach the computer to find cat pictures on the internet. Yes, all this processing power. And you really know Google knows their audience, right? They're pretty much data mining cat pictures. That's what the internet is for, anyway. And this is a representation of what the way the computer sees a cat, or what it thinks a cat is. Nobody told the computer what a cat was, but it just said, okay, look for cats and try to infer which of these all pictures have cats, and try to infer what is a cat in this picture. And it's really pretty fascinating. And I think this is really a sign of the future, where robots are now watching cat videos as well. I mean, that's democratized the internet. Why should only humans watch cat videos? I mean, we're really making progress here. And I mean, more to the point, right? How have we used information security and machine learning to support information security, right? So one of the biggest uses so far of some sort of technique of machine learning has been fraud detection systems. And they have basically been based in anomaly detection. So they're really trying to tell if you have a specific behavior. So given all the dimensions on where I'm trying to gather data from you, so how much you spend each time you use your credit card, how many times you use a credit card per day, per month, per year, which days you use a credit card more, and all this which location you're using your credit card, all these different dimensions, and they'll try to pin you down in a region and space where this is the kind of behavior that you have. So think about a multidimensional space where each dimension is one of these things that I told you about on how I buy it, where I buy it. And if I do something that's too far away from the point where I used to be at, it could potentially flag as an anomaly and as a fraud. This is an oversimplification. I mean, but this is pretty much the basis of where this algorithm started, and still where many of them rely a lot of their decision power on. We have a few challenges with this, because the more dimensions you add, the more all the distances seem the same. It's one of these interesting things that happen in multiple dimensional spaces. But this is why they have evolved past that. But just so that you can wrap your head around this, this is a kind of machine learning. So network anomaly detection, which didn't really make much of a dent in the security industry, they allegedly, at least they would talk about machine learning and things like that, because the computer was making autonomous decisions on what would be good or bad. And I'd be cautious with this notion of machine learning as rolling averages. I mean, my HP12C can do rolling averages, and I don't really say it's learning anything. I mean, this is helpful with some caveats, and does a little bit of statistical analysis, but then this is not machine learning, and usually the people who were doing this sort of analysis would make very, very bad assumptions, such as that the distribution doesn't change, or let's just do standard deviations everywhere, just assuming that there is some sort of normal distribution on what's going on. So I mean, there's a reason why these things are not very popular, and it's mainly because they didn't really deliver what people were looking for. And finally, when you talk about spam filters is the original use case for machine learning and information security. So when people would talk about the Bayesian filters that they would be using to fight spam, there you go. That's the Bayesian filtering. There is the machine learning component of what's been going, of how they were using it. And I'm not gonna really get into this and to explain how them work, but it's all that you need to know is that it's pretty much counting words and trying to guess if a message is a spam or not, based on, okay, it had this word in it, and how many times have I seen this word in a spam message versus in a legitimate message. So that's all there is to it to understand, and as intuition, and they delivered some very good results at the time. And this is one of the points I'm trying to make. And how many people do you see discussing spam filtering techniques right now? And it really seems like people have figured it out, and the performance we get from spam filters now is satisfactory, and it's really doing the job for what we need in a way that we know traditional spam of. Of course, I'm not talking about spear phishing or anything like that, because this is a specifically crafted email that will look like a legitimate one, and will use some sort of social engineering technique to make you click on the link there. That's not spam. The things you sign up at stores and things like that, they are not spam. They're actually, there's a process in which you go through. You have to add some information on the email, and then the spam filters, they have to whitelist. This is actually law in the United States. So apart from that, actual honest to good spam, right? I've had email accounts on the internet for ages now. I've had an email account with Google since 2004, and I'm pretty much convinced that every single spammer on Earth has this email address and has been sending me spams, but I don't get any on my inbox. And arguably, Google has one of the largest data sets of messages, and Gmail is one of the largest email servers on the planet. So it seems that with these algorithms that were put together like something like 20 years ago, and with a whole lot of data, this problem really seems like it has been solved. And this is a little bit of the promise. If we create our algorithms right, and we really understand the type of problem we're trying to solve, as in, we're not trying to solve everything at once. We're not trying to create a general solution to a problem. We humans don't know the general solution to the security monitoring problem. But if we create some tools that will assist us on very specific points, and we can use them to our advantage, and even have them talk to each other instead of just talking to us, we can really make a dent into this space. So, talking about kinds of machine learning, and this is where I want to make sure that we have the proper context here. There's basically two large groups, which were called supervised and unsupervised learning. And the point here on supervised learning is that in addition to giving the data to the program, in addition to giving it, okay, these are the numbers, this is how much someone has spent, this is how much, this is where they spent it to. You're also telling them if a behavior or if the piece of information is something like A or something like B. So let me give you an example. You're trying to tell apart a chair and a table. You're teaching the computer what a chair is and what a table is. So you might give it a bunch of different measurements of chairs and the material the chairs are made of, and the same thing about the table, how high they are, and all different categories and all different information. And you're telling this is a table, this is a chair, this is a table, this is a chair. So then it can figure out once it gets a new set of data on measurements and materials and all the things like that, it can try to guess, okay, this is based on the information you've given me, I believe this is a table, or I believe that this is a chair. So there's two big groups there in supervised learning. One of them is called classification, which is pretty much what I was describing earlier, which means this you have a number of labels, usually two, where you have all this data and you try to classify if this is going to be type A or type B. When you talk about regression, and it's a funny name, it came from linear regression, which actually has nothing to do with regression, but it was chosen like that a number of years ago, hundreds of years ago, and it just stuck. We are actually looking for a measurement on how much something is type A or type B. So, for example, if we were in this chair and table example, if we were using one of those stools that people use to play piano, right? They are very short. They're obviously meant for a person to sit at, but they really look like a table when you look at it. So a computer might get confused with that. So if we, in our program, we were giving the numerical value 0 for a chair and the numerical value 1 for a table, it might guess that this piano stool is something like 0.5 or something like that. And that's the regression problem. We're really trying to find a measurement on how something is like A or how something is like B. And that, of course, can be transformed easily into a classification problem. They're all related in that sense. The other kind we have is unsupervised learning, which you're just giving the data to the computer. You don't really know what these things are, or for some reason you don't want to tell the computer what these things are, so that it can give you its opinion on what's going on. So there's two main groups around that. One of them is called clustering, where it's pretty much what I was describing earlier about the fraud detection algorithms. You're given a bunch of data and you're trying to figure out if you can classify them into meaningful groups, right? So all these things here are similar, all those things here on other point of space, they're similar, and this is very classical, but it's also very, very abused. Clustering is actually a very difficult problem because most of the algorithms, they have no idea how many clusters you're giving them, and you have to tell them how many clusters you want them to guess, which kind of defeats the purpose, right? If you give it to the computer to figure it out, how many clusters there are, you don't know as well. You're just guessing, right? But of course, there are techniques to try to make this a principled process, but it's not uncommon for people to make bad decisions or think they had a good result when they're actually the computer's not doing anything. They are actually making the decision for the computer, and which pretty much ends up as when they get real data, they will usually fail, because real data and data outside our training environment is usually very, very unpredictable. We don't really know where it's coming from. And finally, we have what's called the decomposition problem, which is so given that I have, and this is a tool, right? The decomposition problem is pretty much a tool for someone who's doing data mining or creating algorithms. is given that I have those features here, and I have this information about a specific problem, which of those features seem to be more relevant or seem to have a higher variability that would really make a difference if I was trying to do a supervised learning problem. So as if I gave it the data I was preparing for the other example of the chairs and the tables, and I fed this to a decomposition algorithm, it would probably figure out that there's a great variability between heights. So the height of a chair, at least of the place you sit at, is much lower than the height of the table, of the top of the table. So it would probably figure out, these are very different, but there's a lot of them in this part and a lot of them on that part. So this is probably a very important decision point. This explains a lot of the differences in the categories that you're telling me there are. So I would definitely choose this one as an important measure on your machine supervised algorithm. So anyway, you have all these different tool sets, you have all this different data, and the interesting thing about machine learning, and it doesn't really matter which algorithm you choose. I mean, of course it does, because different algorithms will have different results based on which kind of data you're using it against. But this is a part of the programming of the algorithm, right? You will test a few of them. You might even keep maybe the top 5 that had a good performance for you, and you will use their decisions as kind of a tiebreaker. So if all of them agree, you're going one way. If most of them agree, you go the other way. But the real thing about this is that it can be proven mathematically that the more data you have, and there's a few caveats around that, but the more prepared data and actual data that really separates those two, the 2 or 3 categories that you're trying to figure out, the better your algorithm is going to perform. So as the figure on the left shows, it's pretty much a diagram. There is always an expected error in machine learning. You're never gonna get 100% result on this. If you're getting 100% results, it probably means that the data you're using is, you have too much data of one kind, you don't have enough data of the other kind. That's not how real data in the world behaves, or at least not how it should behave. But the point is that there's always an error, and the more data you have, your error inside your model, which is the blue line, which is the data you know about and the data that you're using to train the model, they will get closer to this expected error. And the same is true for the outside world. So the red line there, which is data that you've never seen. This is a very strong property called generalization, which, I mean, if you do your machine learning right and you try to understand a little bit what the algorithms are doing, it's a very strong tool proposition that we have in machine learning. The points there, the caveats here, is that we have to be very careful about bias in our data. So we might be thinking that we have a very significant representation of the data that we want to see, but we don't. We're really in this subpopulation here that we think behaves this way, but actually outside of this small world, there is actually a lot of different ideas and a lot of different features that should be calculated. There's not a lot we can do about variance. It really depends on the problem, but we really have to be to understand that there might be biases, and we have to look for, if we're really trying to tackle a problem seriously, you have to try to look for a data set that's as diverse as possible, that comes from as many different places as possible. And the other thing, which, I mean, it's not exclusive to information security, but I am confident that it will be the place where it's going to manifestate sooner rather than later, is adversarial intent. So where someone is actively trying to confuse the algorithms and the agents that we have in ways not dissimilar to obfuscation techniques on IDSs and things we get to evade firewalls. So when people understand the way that a specific system works, they will try to figure a way how to circumvent it. I mean, think about the first time you as a security practitioner learned what a buffer overflow was and the way that people used to circumvent the program flow and to execute whatever their own code was. I mean, I was mind blown. I mean, it was many years ago. I was just a kid, but this is the kind of thing I'm talking about. People will figure out ways, and there are ways, already documented ways to potentially confuse an algorithm like this. Just feed it bad data, right? But people will find very creative ways, and this is something that anyone, not only me or ourselves, and anyone who's really serious about doing some sort of machine learning with information security data has to be very aware of the adversaries. And this is not going to be a garden of roses or anything like that. And a good example that I have, it's something that has always amused me a lot, was the way spam filters evolved. And the interesting part is that they would on the early years when the spammers understood how the Bayesian filters work, they just started generating spams which had pasted the works of Shakespeare at the bottom, and that pretty much failed every single algorithm test. I mean, how many spams do you see with the word thou, with the word maiden? So they would really get confused, and they would let the emails go through because it was obviously, it didn't have enough words that would be tagged as bad, and had a lot of words that it either had never seen or they would be tagged as good. We got past that, but this is one of the ideas, one of the ways, one of the examples how people would try to circumvent what's going on. So now that we've gone through the basics and through this cautionary tale of adversarial intents, I want to go a little bit about one of the algorithms that we have developed. And I mean, there is a little bit of math here, not a lot, but you'll soon see that the focus here is not so much on, oh yes, I use this algorithm here, because that really only takes a few minutes to run. The problem is making sure you have meaningful data and data that can express a relationship between your data so that you can use it to infer something. So anyone who's serious about machine learning or has really done this in the past will tell you that you will spend 95% of your time preparing the data, making sure you have good data, and making sure that you can have statistically significant data in order to really make inferences. But anyway, let's get to it. I'm pretty sure you're tired of this history lesson on machine learning. So on this specific example, we trained our model using firewall block data from the SANS DShield project. For those of you who are not familiar, the DShield project basically gathers external firewall logs, information from a lot of different contributors. So people will volunteer and send their log data to SANS so that they can aggregate it, anonymize it, and use it to provide a whole lot of different services on their websites, like which are the ports which are being most port scanned, or which kind of IP addresses or even places on the internet where most of the attacks are coming from. And the fact is, and they were very kind, I do thank their contribution. If you ask nicely, they will let you have access to the bulk data, which is also anonymized, but it provides a breakdown for each day on what each IP address. So basically, if you see the example here on the screen, we have what each IP address did on a specific port, on a specific protocol, and the amount of times that people saw activity from this IP address throughout this population of people who have contributed to their log files. So I know firewall logs sound a little bit underwhelming at first, but one of the points we're trying to prove in this presentation, and with this specific example, is that even with something that you don't really perceive a lot of value, even with data that you believe that, you know, I have absolutely no idea why I should be even logging this, there is some value, actually a lot of value that can be extracted from it in order to help your decision making in using this data properly in information security monitoring. And there's some interesting things about this data that you may or may not notice. First of all, it's diverse because we're not really gathering information from one person. There's a whole different host of companies who are contributing, although SANS will they will not really detail how many there are or where they're from, which I totally respect. But my guess would be, and from the results we've been getting, that the companies who are participating in this project, they're mostly US centric, which talks a little bit about the bias problem we were talking about before. But it's important that if we understand what we're up against, what kind of data we're using, I mean, there's ways we can work around this. So just so that you can have an idea, we've been gathering this information for the past 7 months, and we started on the 1st of January of this year. And we have a mean of 1 million observations per day, which pretty much an observation would be a line on the previous slide where it said that this IP address detected this specific port a number of times. And when you aggregate all this number of times or the amount of hits each IP address did on a specific port, you'll get on an average of 26 to 30 million event logs where this summarized data came from. So it's a good number, but this is not big data by far. So if you have something like this, I mean, I was doing these calculations on a laptop, right, and in some machines in Amazon. So this is not impressive. This is not what big data is for, but it's still a significant amount of data that could potentially be used for machine learning, and this is exactly what we did. So one of the first intuitions on how we put together this model was based on proximity. And like I said before, there has to be some sort of relationship between the data. And anyone who has done security monitoring and being in a SOC at an incident response for some time will be familiar with the concept of bad neighborhoods. You will be kind of trained almost by instinct to pay more attention to specific IP addresses in specific places, because you've just seen a lot more things coming from that direction than otherwise. And of course, there's a whole lot of different reasons for that. It might be that some specific group is targeting you, but the general one of the most general ideas is that there are actually some places on the internet, some ISPs and some hosting providers, that they will be more lenient on hacking behavior or attack patterns activities on their subscribers than others. So if you sign up to one of them and you start doing weird things, you'll get a letter. People will shut down your access. They'll figure out you're up to no good. But some of them, they don't really care, and that's where attackers will, in a way, either consciously or unconsciously flock to in order to use their services. So which might be as anonymous proxies on this environment, so that a VPN there, or they log in there and they use that as a springboard to their attacks, or it's just a place where they can get an IP address from their ISP. So there's a few things to support that. And a recent popular one was the recent fight, so to speak, between Spamhaus and Cyberbunker. So Spamhaus is the spam clearing house. They will have all sorts of blacklists about spam activity. And they recently said to their subscribers, and actually to the internet in general, okay, we quit. We don't want to do anything with the cyberbunker people, which is an ISP in the Nordics. I'm not quite sure which country they're from, because they will not do anything to secure the network. They are not interested in securing it. So just assume that anything that comes from them is malicious. Don't even bother to accept emails from there. Of course, a lot of people have a lot of strong opinions about this, and I don't want to really to get into that debate. But the point here is they realized the pattern, right? That there was a specific place on the internet where more bad things were coming from than another one. And that had nothing to do with the country it was from, but it was the ISP that in a way was promoting this, or maybe not fighting this with enough diligence. And this was also been supported by the recent Google Transparency Report, where they're talking a lot about this aggregation of malware domains. So yeah, we found that malware domains were more likely to happen on these specific ISPs and these specific autonomous systems. And that could be used as a decision. They are using this as a decision metric on their algorithms on how to, on if something should be blocked or shouldn't be blocked by their filters. And finally, there was a paper from a PhD in Brazil, which did a similar statistical analysis about the likelihood of things coming from this place or that place in the internet based on 5 to 6 years of data from the Brazilian University Research Network, which pretty much reached the same conclusion. It's a good read. It's an interesting paper. So given this, and since we're feature selecting, we're trying to figure out what to use, right? Why don't we start grouping the information we get from SANS as by net block, so just an arbitrary measure of /16 or /24, and also by ASN, so the autonomous system number, which organization or ISP they are registered against. And for that we used the Team Kimru service, which was very, very helpful in order to look up which ASNs the IP addresses are from. And you will find something like this, which I think really illustrates the point of what we're trying to talk about. So this is actually a diagram. This is a map. It's based on a construct called the Hilbert curve. And I'm pretty much drawing the internet, plotting the internet on this slide, which is pretty awesome if you ask me. The point here is that what this Hilbert curve will try to do, and you see this line here, this drawing on the gray background, it is pretty much trying to, if you think about the IP addresses from 0000 to 255, 255, 255, 255, as if they were in a straight line. Okay, and for each increment, you're just adding 1 to the octets, and you try to bend this line in a way that you're trying to promote proximity. So I want to make sure that I'm doing a projection here. When you think about maps, and that a map of the Earth is actually a projection of the circle of the sphere in a specific way to maximize or to minimize some sort of distance. What I'm trying to do here is with this Hilbert curve is to minimize the distance between IP addresses that are close. So I'm really promoting clustering here. So if an IP address is near each other, they will be drawn as close as they can according to this curve. So, and what this is here is showing is for each blue dot, I have in this specific region there, I mean each pixel here will be a /24 probably. For each blue dot, I will have had activity coming from a specific IP address there that was blocked on port 22. So someone was port scanning or trying to brute force SSH servers, and they came from these specific places. And as you can tell just by looking at this graph, there is a clustering pattern, and there are places that are more likely. You have brighter dots, you have more dots close to each other than others, and that could potentially be used to our advantage. I mean, if you're really looking for patterns, you can even find some actors here that people really think that are up to something, right? I made a point of putting Brazil there, which is the country where I'm from, so that people don't think I'm nitpicking. But yeah, they seem to be very active there as well. And of course, you can try to look at all sorts of different behaviors here. And this is just counting how many times a specific AS shows up on the first 10,000 samples we get. And we see a lot of Brazil, we see a lot of China. And but the point here, the point that I'm trying to make is we shouldn't really ASNs is actually a good measure. You know, you can make an informed decision on where things are coming from, as opposed to country codes. So if we were going for the China or the Russias of the like, we would be losing actually more than a very huge part of the attack, the threat surface, which is actually coming from the US, right? And even though, and this is US-centric data, of course, US is attacking US all the time. People will have environments there they used to attack, even if they're not from the US. So we just have to be careful on how we choose our proximity measures, and we don't really look for patterns that aren't there, or try to validate the patterns that we really want to see in the data. So, but anyway, the point here is things are not bad all the time, right? Even bad neighborhoods, they will renovate over time. So if someone is attacking you from a specific place on the internet, that doesn't mean that they're going to be attacking you from that specific place for a very long time. Maybe for a while, for a week or so, but they might move on to another target, they might get bored, they might change their ISPs, they might do all sorts of different things. So not everyone is out to get you all the time. I mean, we would be just creating an infinite blacklist, and we would be pretty much in no time blocking out the entire internet, which would be a very effective defense measure, but we also want to actually deliver services to someone, so we can just block off the entire internet. So what we try to do is to forget, and we have a decay function around this actual activity. So if something happened in a day, it makes something happened yesterday that makes it's much more important to me. It makes much more sense for me to remember this than if it happened a month ago. So here's some ideas of functions that do that. And for this specific example here, I've been using a 7-day decay half-life function, which means that after 7 days, I'll remember about half a chance of remembering the specific IP address. And you can see that after 4 months or 3 months, it pretty much doesn't really matter, right? You don't really need to bother with whatever happened. So, but if someone kept showing up, so if something just happened 4 months ago, yeah, you can ignore that. It was the guy with bored. It is something else, or move to a different IP address. But if something's coming from a specific neighborhood every single day or every single week, you'll make sure not to forget it, because the idea that this thing happened will still be fresh in your mind. So given those two intuitions, we start calculating those features, right? So first of all, we have to in a way filter and cluster the data and choose a specific behavior that we're trying to predict. So as in the previous example, what I was trying to show, the point I was trying to come across, was someone who looked like was attacking port 22. And that could be a valid behavior we're looking for. So if we take that into consideration, and we use those people who attacked port 22 over time for a specific behavior we're trying to predict. So it's like we had a specific agent, a specific robot, that the only thing it knew how to do, but it sure does it very well, is to figure out if I have seen someone before like this guy who was banging on port 22. So given this filtering, then we start calculating the ranks like this I described before, based on the clustering and based on the decay. So if I see something on this day, I will tag a value of 1, which is completely arbitrary for that day. And I'll also tag a normalized value of this to their net blocks and for their ASN. So each IP address will have a smallish contribution on each one of those values inside the ASNs, which is compatible with how many IP addresses are in that range. Of course, you still have some missing ASNs. There are service failures or things like that. There are IP addresses that shouldn't exist. So these guys, they just get a bump up on their score, and because they're usually up to no good anyway. So, like I mentioned, you do this for each day, right? And each day is actually will be accumulated. It will be something that will be ongoing until that day from the beginning of our calculation, which is January. So if something happens in day 1, right, you will mark 1 or any specific value for the IP addresses that happened. And then for the following day, you're going to decay these numbers you have here for the using the decay function that I showed before. So it will go to 0.9 maybe, or 0.8 or something like that. And then you will add another 1 or another item to the IP addresses that didn't happen on the following day. So then you will preserve what it looked like, what the calculation looked like on each single day of your history, and you'll make sure that you're forgetting things that happened for a long time and never ever happened again. And it is important to preserve this backlog of calculations, because when you're actually doing the training, which we'll talk about in a little while, there will be log files for multiple days, right? You need to have a minimum of data. You need to have a minimum of observations in order to have a model that will properly converge and generalize. So you have to make sure you have the right amount of observations on the log data, and that for each one of these observations, you're actually using the calculation, the rank calculation from the specific date it came from. So if you get data from the future in order to train a model, you will have all sorts of survivorship biases. You will be counting on something that didn't happen yet, that will, on the best of possibilities, destabilize your model and make it do some weird things. Or in the worst, it will give you the impression that the model is performing much better than it actually is, because you're trying to predict the future with data that actually happened in the future. So yeah, that's actually pretty effective. I'm just telling you what happened. I'm not really trying to predict anything. So this is also something that's very important. It's a very key part of the algorithm. And the reason why it was chosen to do like that is because since we're using log data, it's a very good it's a very good platform to actually do incremental training. And pretty much like you have time series data from stock markets, and people train in history for years and years on end in order to feel confident to make a prediction further on. We can use the same techniques here by having different training models, training different models actually in different points in time, and testing the accuracy of that against different dates on the log data. So this is an example of these calculated features and how they have evolved over the months. And as you can see, after a few months, after 3 months or so, and when you get around May, it really evens out. It really stabilizes as far as the shape, the mean, and the median, because now we're really starting to churn the data that has never happened after 4 or so months, and these things, they get so close to zero that they get ignored. And it's interesting to see the pattern here. And this is actually the horizontal axis here is, the vertical axis here is actually logarithm. So when you get a 3 there, it actually means that it's 1,000, and the 6 actually means like it's a million observations. And no matter what happens, there will be at least 1,000 or so people, as you can see that has a rank of 1. A rank of 1 here on this normalized calculation means that these specific actors, they were trying to attack you every single day. So every single day for 5-6 months, this guy was there and trying to hit you. And yeah, this would be incredible candidates for a blacklist. And even if you were, okay, I'm going to recycle my blacklist every week or so, you would only get here on this diagram until you get like to 0.6. So on the best of days, you would have like, I don't know, maybe 10,000 IP addresses on your blacklist, and that's all the knowledge that you kept there. But when you look at this model, and what this model is trying to express, it is actually condensing knowledge from almost a million IP addresses, with the likelihood of they appearing or not against attacking you, based on the time and when they did it last. And you get a lot more expression here, and you can do a lot more fancy things than just blocking an IP address because an IP address happened. And this is a similar diagram. This is now port 22. The other one was RDP. And you can see the same behavior there. There's always a few guys who will be always out to get you, but the real interest and the data that we lose if we're doing traditional information security monitoring are the ones which are closest to 0, which we could be leveraging to make better predictions if someone is attacking us or not. So just want to make sure we get a briefer here, and there's a lot of diagrams, a lot of math, and let's just pause for a second here before we continue. So finally, we have all this calculation that we did, which is pretty much the features, and we also have a label, right? If those behaviors, if those specific actors, they were blocked, we can definitely tag them as malicious. And now we have, if you remember back there when we were talking about the machine learning process and the kinds of machine learning, we have features, we have labels, and now we have everything that we would need in order to train a model, right? So we just want to make sure we get enough calculations. I was telling about the actual fact that we might need more than one day, and this is where the different day calculations, they make sense and they come into play. And let's get, I don't know, about 100,000 points and something like that to make sure that we can offset any overfitting, and that we have the properties we were discussing before. But then there is a point here. We also need the other label. We also want to make sure that the computer is able to differentiate what is malicious from what is non-malicious. So we need to gather IP addresses which are understood to be non-malicious, calculate the features for them, and then provide them for the computer to be able to train. So what we used is, in this specific example, was data that was gathered from both the Chromium and top 1 million IP addresses list, and Alexa as well. So they got a list of the websites which are most visited, and it's interesting because it's actually from all around the world. So you will get a lot of stuff from China and Russia and things like that. So you don't get US biased in any shape or form. And these IP addresses are then tagged to be good, to be non-malicious, as far as our training model is concerned. And then we get to the actual model, right? Then we get to the actual machine learning part of this whole talk. And funnily enough, it's the least important one. Like I mentioned before, we really want to be able to have meaningful features. So specifically for this algorithm, we are using an ensemble of support vector machines, which is a specific class of algorithms that are very, very good for classification problems with numerical features, which is pretty much what we're talking about here, right? We have two labels, and we have a bunch of numbers, and they're very good into telling these things apart. And the interesting thing about support vector machines, and they're 20-year-old, right? It's interesting, right? They've been around for a while. is that they really try to maximize the slack between your data. So you don't know everything, you don't know where exactly every single data point is, but from the ones that you know, you try to make sure that this surface that you're using to separate is the furthest away from all possible points that you know. So if you do make a mistake, if you do have a point there, at least you get some sort of slack here, which is very, very experimentally, it's very interesting and works out very well. And it also does these calculations in an infinite dimension space. It's really, really crazy when you think about it mathematically. And the mathematicians, they don't really care if the space exists or not. They just know that if they can calculate, if it exists, I can calculate a dot product, and they use the dot products on the calculation of the matrices here. So it's pretty cool, and it works. And how well does it work, right? I guess that's the point. And so we're training this model for each day. Like I said, pretty much like I have a day calculation of the ranks, I will have a model calculation of the ranks so I can test its accuracy against the following day, right? We want to make sure that we have something that's consistent and something that seems to be working or even improving over time as the whole, as the amount of data that I have on a specific environment improves. So what we're seeing here is that the actual training accuracy, and using a technique called cross-validation, which pretty much tests the data against itself while it's being trained, we're getting something from 83 to 95%. And the variation is from different models, from different behaviors we're trying to predict. So for a specific port, you might get a higher accuracy. For another port, which you have less data, for instance, you'll get a worse one. And but that's not enough, right? We want to be able to check in a real world scenario. So, and when we're predicting against the following day, not just the cross validation training inside the training data, we're actually getting this a little bit worse, which is expected, right? We're exposing it to new data, but it's still pretty good and still pretty sound for a machine learning algorithm for what it's trying to do. And talking about 75 to 95% may not make a lot of sense, but we'll get to that. The point here is that, as you can see, there's a clear relationship between the data that you're training on and the power that it has to predict on the future. And so if something in the graph on the left, right, if you have something that was trained on February, it will do a very lousy job on trying to predict what's happening in late July. But as you can see on the diagonal here, and you can see the diagonal is always also represented here on this line graph on the right. Over time, the overall accuracy is improving as we get more and more data, and there's more and more understanding on what is the attack surface that this group of companies is suffering. And you can have a similar graph and a similar idea on RDP on a different port, which, as you can see, that it will lose performance as time goes by, and this is one of the reasons why you have to keep renovating the amount of data, the data that you have, the observations that you have, in order to continuously train the model. So the important thing about accuracy is that it doesn't really tell you a lot about what it means. So I can tell you something like it's 80% right. So yeah, that's only telling you that's 20% wrong. So let's try to break this down a little bit, and I think this will make a little bit more sense on what this results actually mean. So using the examples before, we had that we got it right, let's say 80 times or 90 times. So we can actually break that down using some constructs from people from clinical trials and even specifically statistical tests, where we have a 70 to 92 true positive rate, which means something was bad and we recognized it as bad, and a 95 to 99 true negative rate, which means that something was good or non-malicious, and we recognized it as such. So if you do given those results, if you do a calculation, it's called the odds likelihood, which means given that I have these rates, how likely it is for something to be bad if I tell you it's bad. We get a result that if these specific agents, they point out to you that something is worth looking at, something is malicious, it is from around 14 to 18, 19 times more likely to be bad, right? There's an increase in almost in 15 to 20 times relevance for your analysts, which could be on the job there. They're trying to figure out which events to investigate. And you can tell, okay, from my observations over time, these guys are much more relevant for your, that you should look at them right now. So the idea is if you only got time to look at 10 guys, look at these 10 guys which were rated the highest on the probability that they might be out to get you. And here is a representation of that. And again, this is the Hilbert curve, and which we shown before on the same port 22. So on this specific example here, we just did, using what we have been constructing so far, we did a trial inference on 100,000 IP addresses per class A. So each square there is roughly a /8 on the internet. And okay, let's select 100,000 of these guys. Let's run our predictive model against them and try to figure out what are the chances that these guys would be attacking us. And this is a logarithm scale, so that you can see on the right side of the graph. But the point here, the brighter the tile, the more likely it is to be out to get you. Someone from there is out to get you. And the brightest tiles can be 10 times to 1,000 times more likely to be attacking you than other ones. And if you remember our friends here, you see, some of them are high, but they might not even be the highest ones in their neighborhood there. And but this gives you a much more clearer view of what you should be preparing against, or who you should be preparing against when you look at this situation. Anyway, nothing is perfect, right? And there are some very easy to see criticisms to the way that this was put together. And first of all, the IP address thing, right? And it's not as reliable as it could be. And when people are doing incident response, specifically for attribution, they don't really believe in the IP addresses because of course, people will hop around the internet. It's very hard to trace back. And of course, UDP is completely out of the question because it's so easily spoofed. But the point I'm trying to make here is not about attribution, right? I'm not really trying to figure out who's attacking you, but to be able to provide a better way for you to defend yourself. And attribution it's a complicated thing, and it goes way into the realm of more advanced incident response. But when you're talking about helping the right information to get in the hands of the incident responders in the sense of what they should be looking first, this is where something like this really, really helps, right? So you might have some challenges when you think about anonymous proxies, but in the specific case of anonymous proxies, not really, because the kind of behavior you'll see on ISPs allowing anonymous proxies to exist will be quite similar to the ones from people who are just making bad stuff locally, right? It's the same problem. Attacks are coming from this IP address. Should I allow that or not? When you go to Tor, it gets a little bit more difficult for the clustering behavior. You can't really predict it as well. And I mean, if you're just using Tor and you're switching your IP address every 15 to 20 minutes, it would be very hard to pinpoint an attack because it would be all around the place. It could be interpreted as noise by one such algorithms. So for these specific challenges, there should be some other supporting agents or supporting mechanisms to help prevent against those things. But this whole idea, this whole algorithm was actually designed not with IP addresses in mind, but with a way for you to identify an actor in a log file and to cluster them in some meaningful way. So we're just discussing about IP addresses here in this example, but there are many other ways which you can cluster different kinds of data and get even more meaningful results that would defeat this weakness around IP addresses. So as far as going forward with this, there is, of course, like I said, there is a clear advantage to help the lower tiers of a security operations center, the people who are actually looking for the logs and trying to pinpoint things that the more senior analysts would then investigate and search and try to do some sort of instant response on. You can't really eyeball all of the data, and that's the point I've been trying to make since the start of this talk. So, and when you get some of these agents that are communicating with you about things that they believe are more likely to be attacks, you start to get an increase in productivity. And it gets even more interesting if you start getting those agents to talk to each other. So if one of them is predicting against port 22, right, hitting on the firewall, and the other one is doing the same kind of behavior, the same kind of prediction around failed authentication on SSH and specific usernames that are being tried, and those models start talking to each other, you can get an even higher degree of confidence, because if something is tagged in one of them and has a 15 times more chance to be there, and it gets tagged on the other one as well for an additional 10 times, now you have a potential attacker which is it could be up to 150 times more likely to be attacking you. And then maybe you can make a decision like, okay, I am going to block this guy because 150 times is way too much. Or I'm going to do some SDN trickery here where this will actually go through a longer path in my network, and I'll have additional controls there that would potentially help me catch this guy, or maybe even a honey net. So it gets really interesting when you can get some of these agents talking to each other and making decisions in tandem against what would be the better way to protect your network and who are these potential malicious actors. And just to wrap up, I wanted to talk about the project that is actually developing those algorithms and testing them out. And you can see the address on the website. We are mainly looking for data, for people who would be willing to share their data with us so that we can train the algorithms and run the algorithms against them, and then provide back some reports based on these results so that you can start testing using them together with your current process, and even help us improve even better by pointing out, okay, this really worked, or this didn't work so well, so maybe we should try to figure out why this is being tagged as malicious when it really isn't. So you have the contact information there, and just let us know if you have the interest of sharing your data and getting those reports back based on as this research continues. And anyway, here the points here, and this is the thing I want people to get out of this presentation, is that machine learning, it can help, and there's not a lot of people who are looking at this right now, but it can definitely assist monitoring teams in data intensive activities. We're looking at a lot of data, and we're going to need support in order to make sense of all of this. And even these initial results that we're sharing here of 12 to 18%, 12 to 20 times likelihood, it is a proportional gain you would get on your monitoring teams. If they're just there looking at random at IP addresses, or trying to make sense of a whole lot of logs, or a screen full of red alerts on a SIM dashboard, they now can be much more focusedly directed on things which are more likely to be attacking you, and gain on efficiency. And anyway, like I mentioned, this is just the beginning, and this is only one of the algorithms that we have been researching recently. And anyway, thank you very much for sitting through this. and just ping us, send us an email, and let us know what you think and if you think you can contribute to the project in any meaningful way. Thanks.